In this lecture, we will start talking about the standing wave ratios, and somehow we have discussed the standing wave ratios in unit third when the waves are moving in the unbounded media. So now we will talk about the standing wave ratios in the transmission line as well. So here we have, if you have the transmission line, for example, here, if you have some transmission line, so the transmission line, the voltage and current, the are function of this location of the transmission line, that is the spatial coordinate. So the voltage is given by here. This is the voltage on the transmission line, where you have the total voltage is the sum of the incident voltage and this is called the backward traveling wave or the reflected wave. So then you can uh, write this expression as, you can take out the V naught plus common and it will be 1 plus, and before that what is here, V naught negative is you can write this one as, you know that V naught negative over V naught positive, the reflection coefficient at z equals to 0, which is given by here. So you can write V naught negative equals to gamma naught into V naught plus. Once you write, you can take out the gamma, so V naught plus to be common. It will be 1 plus gamma naught e to the power j 2 beta z. You can also take it out the e to the power minus j beta z. So this is the expression here, or you can write this is as V naught plus e to the power minus j beta z, and here you have 1 plus gamma naught e to the power j 2 beta z. Now if the load is connected here at the end points, that is a ZL, then this gamma naught is also called the gamma L, that is the reflection coefficient at this point where the load is connected, this point, and this gamma L have the magnitude and the phase, so you can write it as V naught e to the power minus j beta z 1 plus gamma L magnitude, and you can write this one here. So what we have, you can write here as e to the power j beta z 2 beta z plus phi L. So you can add this, the phase of this to this one. So I can rewrite here this VSZ, and here you can go through. So what do you have? You can switch to this one. Let's take to the blank page. So here we are. So we have, let's take the pen to be, this transmission line here, and the load is connected at this point. So this is the transmission line here, and this is the z-axis, along the z-axis, and you connect a load here. The load is connected at this point, ZL. So the total voltage, and the total voltage is given by, as we have obtained, total voltage is given as V naught plus for minus j beta z, and here this will be 1 plus gamma L magnitude and e to the power j. The phase will be added. This is 2 pi z plus phi L. This is how you can write this expression. Similarly, you can see that for the current I as Z. So here what you have, it will be just what you will here. This is V naught over Z naught before minus J beta Z, and here it will be minus V naught negative over Z naught e to power J beta Z, and when you simplify it, you will get 1 over Z naught and V naught plus it was J beta Z, and here it will be 1 minus gamma L e to the power J 2 beta Z plus phi L. Now S is defined as, we have seen that how the S is defined. So you have this, the standing wave ratio is defined as V maximum over the V minimum, or the I maximum over I minimum. So when you see here, so what is the maximum value of V, and what is the maximum value of I, and what is the minimum value? So to understand that, just have this one. So what you have, let's take another page. So here you have, this is the page width, view as a whole page. So here what do you have? Let to understand what is maximum value. If you have some complex number, so it will have some magnitude and it will have some phase phi. So if you draw in this coordinate z space as a complex space, so it will be a real part and it will be an imaginary part. So how to map this complex number on this coordinate? So this just is, you can take another pen. So let's take this one. So it will be at some point here, and whose magnitude is this R, and this is the phase phi. So if we fix the phase, that you have you take again this somehow pen. Like this one. So if, for example, some complex number is given by, you have R is varying, and where the phase, for example, this is 0, that is a real number, so R. So when you map, this whole number will be mapped onto this axis. This phase is 0, the phi will be 0. So whatever all this line will be there. So for different value of R, you will have the point lying on this real axis. Similarly, if you have some phase, for example, you have e to the power j, for example, more than 90 degree, let 135 degree, then it will be mapping here on this line. So this angle will be 135 degree, and all the points on this will be mapping to this equation. So for different value of R, you have this here points. Similarly, if you fix you have fixed the R, for example, you have 1 e to the power j phi. So what it means that you have some, this is the magnitude is constant and phase is changing. For example, magnitude is 1 here. Now if you vary this phi, so it will make this circle. So this magnitude remains same here, this is 1 unit, and different value of phase phi will change according to this one. This phi is variable, so this will hold, all the points of phi will map to this whole circle. Similarly, all the points of R, where R is ranging from 0 to infinity, so here this will all lie in this line, on this line from here to infinity. But here when phi is varying, so phi from vary from 0 to 2 pi, so you have 0 to this, phi is 0 to 2 pi, so it will map to this circle, on this circle. If we more than 2 pi, again it will be repeated. This is how you understand the complex number. Now adding two complex number. For example, now you add these two complex number. So we have Vsz equals to V naught e to the power minus j2 beta z. Sorry, beta z, and here 1 plus gamma L e to the power j 2 pi beta z plus phi L. Now here you have two complex number. So when you take the magnitude here, so the magnitude of this part is V naught, and here you have to take the magnitude of these, add two complex number when you add it. So when you see on this complex domain, so how it will look like. So this one is a real quantity whose phase is 0. So this one will have fixed point. So it will be a fixed point here. So let's take some another this one. So we have this point fixed 1. So here this is 1. This is a 1 quantity. Now you add this one. What is this one? This one is a, this is let's take another pen here. So let's take this one brown. So this is a, here this is a magnitude which is fixed. Once the load is connected, the magnitude will, you can calculate, and that will be fixed. So magnitude fixed, but with the different value length of transmission line at the location, do you have a different phase. The phase will change. Though phi L will be constant, but that will change. So this will, for example, you have 1 plus zero point 0.5 something e to the power j. This is the let phase some phi. So this value is magnitude is zero point 0.5, and this is value with phi. So here it will map to this somehow this circle. Now when you add this one, real part will be added, and also the imaginary part will be added. So here you have only real part, and here it will have the real and imaginary. So it means all the points which are mapped here will be shifted in the real domain. So now this circle will be shifted at this one. So when you redraw this one, when you redraw, when you redraw this here on this axis, so you will have a circle. This is the point here. So all the values will be mapped for different value of z. The point will map to this circle. Now, for example, for particular value of z, you have a point here. You will be, so it will be 1. This will be added 1 plus this magnitude and this phase. Now, what is the resultant complex number? The resultant complex number will be this much. This one. So for different value of z, this value is fixed, this distance, this magnitude will remain same, but the phase may change, so this will map different values. So for any particular value of z, this length will change, this vector will change. So it will be maximum when these two distance lines are aligned. That is, if you have the this value is such a phase is such a way that this is 0, and this distance will be aligned z-axis, so this will be the maximum. So this will be the maximum. So maximum value of V as Z, magnitude will be what? Magnitude will be the when this is maximum. This will be fixed. This is V naught plus. The maximum value will be V maximum. You will have the V naught plus this. This is the magnitude of this one is the V naught plus, and the magnitude of this one is the here what you are getting a maximum. So it will be 1 plus gamma L, because this will become 0. So it will have the magnitude. So these two will be added in magnitude. Similarly, minimum value. So you can So minimum value will be V as Z. Minimum value will be minimum when this vector is aligned to here. So when this vector will be aligned here, so you will have, so this will be the minimum value when this point comes to here. What is the minimum value? This minus this part will be the, so minimum value will be, here you have 1 minus gamma L. So this is the minimum value. Similarly, when V as Z is maximum at this point where Vz as is maximum, now the I as Z is given by only the difference of the 1 over Z naught minus J beta Z. So 1 minus gamma L e to the power J 2 by beta Z plus phi L. So at this location when Z is, when this is maximum, when this phase becomes 0, so at that location, at that value of Z, this will become the minimum value. This will be, because we have a minus sign, so where the voltage is maximum at the same location, the current will be minimum. Similarly, the when the current, the voltage is minimum, when this is, the phase is pi or minus pi, then it will become negative and you will have the minimum value of Z. In that case, this current will be maximum. So whenever at those locations where the voltage is maximum, the current will be minimum, and where the current voltage is minimum, the current will be maximum. This you can understand. Now the maximum will occur when this voltage will be maximum when you are having this phase is 0, and minimum will occur, voltage of minimum voltage will occur when this phase is pi or minus pi. So these we have calculated here, shown here in this notes. So when you take the ratio, the standard ratio V max over V minimum, so it will be, you have 1 plus gamma L over 1 minus gamma L. So this is the ratio of the standing waves. So, and the maximum voltage will occur when this one phi L, this 2 beta Z plus phi L is multiple of 2 m pi, or it is a multiple of m pi. So you can find out from Z here that how you can find ZL. So it will be just a here. So Z maximum will occur for this condition. You can find, similarly the minimum voltage will occur when this is odd multiple of pi. So you have 2m plus 1 over pi, then you will have the Z minimum. So when this ratio is the 2m plus 1 pi. So you can find the location where Z maximum voltage will occur or minimum voltage. Similarly, the current will be minimum at this location and the current will be maximum at this location. This is how, what is the voltage ascending wave ratios. Now for shorted line, when you have a line and this line is shorted from here at this point, at the end point, ZL as equals to 0, then gamma L, you know that when shorted line is minus 1, the magnitude is 1, so S, this what you are getting, the S will be equals to 1 plus gamma L over 1 minus gamma L, so you will get the infinity here. Okay. Now similarly, when this line is open circuited, ZL infinity, still the magnitude will be 1 and phase will be 0. In that case, the S will be infinity. When the load is matched, that is ZL is equals to Z naught, then gamma L, there is a reflection coefficient, is 0. In that case, S will be 1. So S will rise from uh, 1 to the infinity. 1 means it is matched, there will be no reflection and thus there will be no standing waves. And infinity means that perfectly the wave is reflected back. All the wave power is reflected back. So when you add those, you will have the infinite ratio. Okay. So this is what do you mean by the standing wave ratios.